Hello viewers, welcome back to the course on scientific computing using MATLAB. So today we will also continue from the numerical differentiation we have started in the previous lecture. So let's continue with the numerical differentiation. So in the previous lecture we have discussed that how we can use the Newton methods that we used in the interpolation to find out the derivative of the function at some value in between the given values. Now we will continue with this one. Today we will discuss the various numerical differentiation formulas. Like we have the data points. So this is my x0, x1, x2 up to xn. So this is the n plus 1 number of points, and the value of the function is given to me. Now suppose I have only this data and I want to find out the derivative of the function at any point in between. So I will try to find out the various numerical differentiation formulas. Now this one we are doing, so this is, I am talking about equispaced data. So I have xi plus 1 minus xi, that is equal to h. Now, so let us take, this is xi, this is x with the, now using Taylor series we can write f at any xi plus h. So this one I can take any constant value plus h. So this one I can write as xi plus h f dash at xi second derivative xi and so on. So this one I take as a 1. Similarly, I can find xi minus h. So this one I am doing as a forward and this is a backward. So this one I can write xi plus this is the question number 2. Now I want to write the forward. So from equation 1 I know that this f xi plus h, that is equal to f at xi plus 1. So this is equal to f I plus 1, right. So this is basically, if I write xi, y I can write yi plus 1, that is equal to f I plus 1. Similarly yi, so add the nodal points. Yi is equal to fxi. This one I know that one. So from here this can be written as fi plus h. Now this is the value f dash xi now from here I will take this term on the left hand side. So once I take these terms I will get these values only, and now I take the common value, that is h. So it becomes f dash xi plus h by 2 factorial f double dash xi plus now h square by 3 factorial f triple dash xi and so on. From here I can divide by hi, so I will get fi plus 1 minus fi, that is equal to h, and now from here if you see, then I will get the term f dash x plus all these terms. So all these terms, it will contain the value of h, then h square. So since h is very small, we choose h very small, so h is very small, then the higher order terms can be neglected, can be ignored, because the higher terms will be very small. So these terms will be very small as compared to this term, next term will be very small. So from here I can write that this one can be written as h by 2 factorial f double dash xi plus other terms negligible terms. Now from here now this is a function, so I take the maximum of this one. So from here I know that this can be written as, so my f dash x, so this is f dash x at I, it can be written as fi plus 1 minus fi by h, and this term, so this is the terms we have neglected, and I take this term, so this will be minus h by 2, and then I take f dash some xi, where xi I choose between xi to xi plus 1. So from here I can say that my function f dash xi, the derivative of the function at xi is equal to fi plus 1 minus fi by h, plus the error term is of order h. So from this is the same as we have done for the forward operator. So I am taking the value of the function at I plus 1 minus fi divided by h, and this is, I know that the derivative is of order h. Similarly, we can find backward operator. So I can use the previous one. So using this one, the same way I will go fx minus h, it will take on the left side, I will take the minus sign and so on. So from equation 2 I can, so from equation 2 we can write f I minus 1 fi minus fi minus 1 at xi plus the terms order of h, because everything will be same in this case. So all the terms I will take on the left hand side, then I will take the negative sign divided by h. So the same thing will happen what we have done just now. So from here I can write that my first order backward difference operator is of order h. So this one we can write down. Now, so this is of order h. Now I want to write the higher order. Now I want to define central. Center difference operator. So subtract equation 2 from equation 1. So, I can write function at xi plus h minus f xi minus h. So, this I have written because I am just subtracting 2 from 1. So, this will cancel out and I will get this value. So, from here I will get 2h f dash xi. Now, this will again this will cancel out and this will be 2 times of this one. And so on. So, from here I can write this as f xi plus h minus f xi minus h, and now I take the 2h common from here. So, that would be 2h is equal to f dash xi plus, so I have taken the 2 and h. So, it will be h square by 3 factorial all other terms. So, next term will contain h cube, h4 and all the terms. Now, from here the same way I can define that all the terms after this, these terms are as h is very small. So, I can ignore all the terms. So, from here I can write that my f dash xi, thus the first derivative at the point xi can be written as f I plus 1. So, this is this value minus f I minus 1, the previous value, divided by 2h plus this is h square by 3 factorial 6, and this one I can write as some xi. So, from here I will get the central difference operator for the first derivative. Now, from here you can see that in this case my error is of order h square. So, from here I can say that in this case the error is of order h square. So, order of h square. So, when h is small, so in that case the error is very small. So, this is, I can say that central difference method will be better for finding out the first derivative for the given data. So, this is the way we can derive the first derivative. Even we can derive the second derivative also. So, this is the 3 first derivative we have defined. Now, I have used the Taylor series methods to find the first derivative at the value xi, using the forward operator, using the backward and in the central. So, now the question comes that can we use other points also, to neighborhood points, to find out the approximation for the first order derivative. So, for that one we have the method that is called undeterminate coefficient. So, in this case this is the method of undeterminate coefficient. So, sometime we are interested to devise a derivative or differential formula consisting consisting of some specific ordinates. Like suppose I have my data is given to me, and suppose this is my xi, this is xi plus 1, xi plus 2, xi plus 3, xi minus 1, xi minus 2. So now suppose we want to use the values corresponding to, suppose this value and this value, and I want to use this value. So I want to devise a formula for the first order derivative which contains only these values, means value of y at xi, value of y at xi plus 1 and value of y at xi plus 3, and I do not want to use the value of this one and this one. So basically I want to find value of f dash at xi as a, the value at xi plus b xi plus 1 and c 3. So this one you can also write as a f at xi plus h, b f at xi, this is xi value, xi (3h). So let us take it 1. Now I want to find the value of this constant that is called the undetermined coefficient. So this constant I want to find out, and then I will be able to get the value of the first order derivative for the given nodal points. Now we know that f at xi plus h can be written as using Taylor series so let us take it 2. Similarly, this can be written as 3h f dash xi this one. Now substitute equation 2 and 3 in 1. So I can write from here a f at xi plus b, and I can write this way plus c by 2 factorial f double dash xi and so on. So now this is the expression, final expression we get. Now from here I can collect the terms corresponding to fxi. Then I can collect the terms corresponding to f dash xi and so on. Now from here I can write this function as fxi is equal to So, I am collecting the terms corresponding to fxi. So, that will come from all. So, this will be a plus b plus c f at xi plus. Now, I want to collect the terms corresponding to f dash. So, if I take the f dash, it will be, so this will be a, no, not a, this will be b plus 3c into h f dash xi plus the same way I can define from here. So, b plus 9c, so this is a 9 xi and so on. Now, now equating the coefficients of same terms both sides. So, from here I can say that I have the left hand side and that contains only f dash and the right hand side this one, and this is true for all xi. So, from here I can say that a plus b plus c, that will be 0, and b plus 3c, that will be 1, and b plus 9c, that will be equal to 0. The corresponding to the terms this h square f double dash. So, the coefficient will be 0. This is the coefficient that will be 1. So, I need the 3 equations. So, from these 3 equations, if you solve, then from these 2 equations I will subtract. So, I will get c is equal to minus 1 by 6. If I put c is equal to minus 1 by 6 here, I will get my b is equal to half to this 3 by 2. So, this will be 3 by 2, and then my a will be minus b plus c, that is 4 by 3. So, from here I am able to find this value of a, b and c. So, that gives me that my f dash at xi can be written as 4 by 3 f at xi plus 3 by 2 f at xi plus 1. So, this is f at xi plus 1 and c minus 1 by 6 f at xi plus 3h. So, that is the expression for the first order derivative that contains 3 points, that is f at xi, xi plus h and xi plus 3h. So, this is I also called 3-point formula for first order derivative. So, in this case I can define the same way we can define the first order derivative using the different points. Maybe somebody is looking for the point so maybe it happened that somebody is interested in finding the derivative at xi using this point, this point, this point and this point. So, that is the 5-point stencil we have. So, that also we can find out, or maybe some other terms. So, with the help of Taylor series we can find out any value of the derivative of the function at any point xi using the neighborhood points that are given to us as a terms of data. So that we can do with the help of the method of undetermined coefficients. Now, if you want to see that how this different type of expression for the derivatives are helpful, so this one I can represent with the help of the figure. So suppose I have this function. So this function is, some function is given to me like this one, and the value of the function is given to me at xi. Next value is given to me at this at xi plus 1. Next is previous one was given to me at xi minus 1. Suppose I take this value. Now if you see at this point the derivative is this. So this is my derivative, the real derivative. So this is my dy dx at x is equal to xi. Now what I am doing, first I am approximating this derivative. Suppose I am doing the forward operator. So this value and this value I am taking. So I take this value and this value. So that is the triangle we are going to have. So in this case, at this point I have xi plus 1 at yi plus 1. This is the point we have xi plus 1 and this is yi. So if I take this value, then I will representing f dash at xi, I am representing by the value of the function at xi plus 1 minus f at xi divided by h. So if you see this one, that is the basically tangent of this angle, this divided by this. So this is of order h. Now the same way, if I am doing this one with the backward formula, so I am taking this value and this value. So from here you can see that considering this value. Now using the backward, I am having xi that is equal to f at xi minus f at xi minus 1 divided by h, and that is of order h also. So that is the, if you see, this is the triangle. So fxi minus fxi minus 1 and divided by this value. Now if I take the central scheme, so in the central scheme, if I want to, so I have this point and this point, so I am taking the line connecting this point, and from here I will get f dash at xi is equal to minus of fxi minus 1 divided by 2h, and this is of order h square. So you can see that this chord seems is parallel to this tangent, so that is why we can say that this center scheme or the central finite difference is order of h square, and it going to give you a more accurate value as compared to the forward finite difference or the backward finite difference. So that is the way we can approximate the derivative of the function at any nodal value xi with the help of forward, backward or the central. So this is the way we can have the approximation. So let me stop here today. So today we have discussed how we can define the forward operator, the backward operator or the central difference operator for the first order derivative, and then we have also discussed that how we can use the method of undetermined coefficient to devise a formula for the first order derivative using the adult nodal points, the neighborhood nodal points. So we will continue with this one in the next lecture. So thanks for watching, thanks very much.